Good afternoon, everybody. Thank you for stopping by for a nice Wednesday afternoon at Chem 170 with your host, me, Dr. White. All right, here's the game plan for today. It's Wednesday. Let me check. Yep, it's Wednesday. And what we'll do is first I can go through the ethers and epoxides problem set, and then we get to go back and look at stuff with aldehydes and ketones. And don't forget, Dr. White, Mother Nature loves aldehydes and ketones. All right, before I start, any questions? In that case, I'm going to get going. All right, thumbs up, people. Does everybody see ethers and epoxides practice problems on your screen? Thank you, Jimmy. All right, let's go through this. The question, and don't tell the instructor, but on test 2, I don't think there are any questions on ether nomenclature. Shh. Remember, don't tell the instructor I said that. All right, let's go through. An important thing is give the organic product or products for the following reactions. And how do you do this? You look at a molecule and look for what's different. What's not carbon, what's not hydrogen should get your attention like this. I have to sneak that in. I did. If we look here, oxygen minus on a carbon was sodium cation and A plus, alkoxide, carbon, 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 ooh, iodine. And that's an alkyl halide. There should be a prime there, it fell off. And you get an ether plus a salt, but since I'm just asking for the organic product or products, guess what? You don't have to put that down. What's R? Methyl, what's R prime? And propyl. Now, this is important. In the Williamson ether synthesis, the carbon with the halogen in R prime, which the R fell off, R prime, is the carbon the oxygen is bonded to. Placement of bonds is very important. Let's look at the next one. Here I also have an alkoxide plus an alkyl halide. And let me write it on my whiteboard. Hold on, let me open my whiteboard. Oops. All right. Watch closely because this is important. Everybody see my whiteboard, what I'm drawing now? Thumbs up, people, help me out. Thank you, Jordan. I think it was a bromine. And the question is, give the organic product or products for the following. What's different here? Oxygen minus side, sodium cation, carbons. That's an alkoxide. Ooh, carbon, carbon, carbon with a halogen, alkyl halide. And this is a Williamson ether synthesis. And you get an ether plus salt. But if I'm only asking for the organic, you don't have to write that down. If you want to, go right ahead. Now, the important part, the oxygen bonds to the carbon in R prime that have the halogen. This one. So this goes like that, attacks that. Organic chemists are violent. We say not bond, attacks. Actually, when you talk with your colleagues, we use that. And here's the correct answer. Now, watch carefully. Make some room here for myself. There we go. And let me change colors so you know it's wrong. and it's wrong. It's on the wrong carbon. It should be on this carbon, not the one it's on. And also, if you look at this carbon, you've got 3 hydrogens, 2 bonds, 1 to oxygen carbon. That's 5 bonds to carbon. And that's no. So placement of where you bond things is very important. And if you were to look at this carbon, it only has 3 bonds, which is also no, can't happen. So be very careful where you place your bonds. Yeah, I grade on that. The one in red is clearly wrong, even though I sort of knew what the student wanted, but that's not the right structure. So please be careful. And that happened on test 1 to some students. All right, let's get back to the problem set. That's not the problem set. That is. And notice I have a few more examples. All right, let's look at D. What do we have that's different? Carbon, carbon, oxygen, hydrogen, hydroxy group on carbon, alcohol. What do we have here? Ethylene oxide. And what do you get? The following ether alcohol. What's R and butyl? And the carbon with the hydroxyl group is the carbon bonded to this O in the CO, CH2, CH2, OH. Not this one, not this one, not that one, only this one. So be careful. All right, let's look at the next one. Oh, look, it's a favorite trick an instructor does on a test. Big, scary R group. But really, this is an alcohol. Carbon hydroxyl group, alcohol. Ethylene oxide, this is what you get. What's R? This. And this carbon is what's bonded to the oxygen, not this one, or this one. And that's how you do it. And here I made even bigger, scary R group. And really, this is an alcohol, R, O, CH2, CH2, OH. Now, the next one, and here, remember when we talked about this in class, ethylene oxide will not react with benzene ring. It will react with an alcohol, and this is phenol, and that's an alcohol. Alcohol, and ooh, coefficient 9 moles or molecules of ethylene oxide gets this polyether alcohol. And once again, placement is important. And here, let's just do, oops, I don't want to do that in red. All right, now something, I'm going to let you have some fun. Give the organic product or products for this reaction. Your turn. And when you're done, give me a thumbs up. Let's try that. Usually I use the poll, but let's see if thumbs up works today. Oh, I got the wrong product. Oh, bad, Dr. White. Sorry. Well, there goes my perfect day. Thank you, Hannah. Anybody else have a thumbs up? Everybody's thumbs up broken. Like, oh, Jordan's works. Let's see if mine works. I wonder where mine are. Anyways, let's go and do this. What do we have that's different? Carbon, carbon, hydroxyl group on a carbon, alcohol. Ooh, 8 moles or molecules of ethylene oxide. And you get this polyether alcohol. What's our ethyl? 2 carbons. Bracket OCH2, CH2. And what's N? 8. And then OH. And this is the correct answer. Everybody, please pay attention. This is a common mistake students do on test number 2. And no such molecule ever existed. It would have 8, 10, 11 bonds to this carbon. It's not going to happen. You find a way of making it happen, let me know, and we'll be rich beyond my wildest dreams. That goes beyond my old islands in the South Pacific, Lamborghini, Countach, and a couple of fighter jets to play with. Beyond that, anyways, the hydroxyl group is always on the outside of these brackets, as you see here. If you put them inside, it's wrong. Placement is important in organic chemistry. Oh, let's try one more. And have fun with this one. What would be the product or products organic for the following reaction? 3 points each. And while you're doing that, I'm going to check something personal. All right. And right at 7, hopefully the Avalanche will do better than they did on Monday. I'll be watching the Stanley Cup Finals. Yes, Dr. White's a longtime hockey fan. If you're a Blackhawks fan, you'll understand that when I was young, my father took me to see the Blackhawks. I think I was in grade school. Yeah. And I got to see Bobby Hall play, probably one of the greatest Hawks. Stan Mikita, Chico Mackey. That's the year they won the Stanley Cup, 63. Whoa, that's a long time ago. All right, everybody done? If you're done, give me a thumbs up. Well, in that case, let's try this. Thank you, Jimmy. Thank you, Hannah. All right, I think everybody's done. Let's do this. If we look at this molecule right here, you look for what's different, what's not carbon, what's not a hydrogen. Ooh, oxygen with a hydrogen on a carbon, that's an alcohol. Ooh, 7 moles or molecules of ethylene oxide. And you make this polyether alcohol. What's R? This. And therefore, I'm going to draw this R. Do you break carbon-carbon single bonds? No. Now, the carbon with the hydroxyl group will be the carbon bonded to the oxygen inside the first bracket. And this should be a 3. And that's this carbon. So, bracket O, CH2, CH2, close bracket, what's N? 7. And then outside the bracket is my hydroxyl group, and I'm done. If you had put this bond to this carbon, I'd mark it wrong. This one is the same as that. I should do better examples. But anyways, placement is important. All right, let's move on. All right, on test 2, coming up, I guess a week from this Thursday, I think. I'll have to look it up. I'll have usually 3 synthesis problems. So let's look at one. And here's one. Give the starting materials for the following reaction. And if we look at the product, what's different? Oxygen with carbons here and here, ether, and you're given a salt, NaX. I don't have it here, but X can be chlorine, bromine, or iodine. In this case, it's bromine. What do you start with? An alkoxide, the alkyl halide. Now, I can call the methyl R, the ethyl R prime, and I'd get the top reaction. I can call the ethyl R and the methyl R prime, and I'd get the bottom reaction. Which one is correct? In this class, they both are. In real life, the bottom one has a lower direct cost, what you pay for the materials, and that's the way to maximize your profits, but you don't know that. And I bet almost all, except maybe one chemist at ACC know that. At COD, I don't think any of the other organic chemists or chemists know that. I do. All right, same thing with B. And B here, ether, I call this R prime, If I do that, then the top is the two starting materials. If I call the isopropyl on the left, right, R, and the N-propyl on the left, R prime, then the second one would be the correct answer. Which are correct? They both are. Now, Dr. White made a mistake. Cross off C. I will never give on a test or the final synthesis problem dealing with ethylene oxide like I did right there. So good news, I made a mistake. Any questions on the ethers and epoxides problem set? While you're thinking, I'm going to drink some tea, blueberry tea from the Republic of Tea. Earlier today, I had my favorite, my vanilla almond. All right, no questions. It's time to get back to aldehydes and ketones. And just to remind you, Carbonyl Group, you should know, carbon, double bond to oxygen. When there's a hydrogen and an R group on there, that's an aldehyde. Carbonyl Group, carbon, double bond to oxygen. When you have two R groups on there, they can be the same or different. This is a ketone. As we did yesterday, find the longest chain with the carbonyl carbon, that's the carbon bonded to oxygen, double bonded, and name it as an alkane. Drop the E, add Al, and the carbonyl carbon is always number one, so you need no number. Now, for a ketone, find the longest chain with the carbonyl carbon in it. And if it's acyclic, name it as the alkane it is, drop the E, add ONE, and you need a number. And the number has the highest priority of anything on a chain, meaning it should be the one that's closest to the end of the chain and the lowest number that way. And you number all the other alkyl groups as we've done before. Now, cyclic in a ring, then name the cycloalkane, drop the E, add ONE, and no number. Since the carbonyl carbon is always number one, it rocks. And that was a quick review. All right, let's move on. Now, switches off, click for this slide, but let's look at a couple of aldehydes and ketones in nature. You've already learned about benzaldehyde, which is the odor and smell, not odor, smell and taste of cherries and almonds at the same time. There's other things there. Now, this should really be trans cinnamaldehyde, which is the common name, which is this molecule you learned about in the lab on spices. And then vanillin, you learned, was an aromatic aldehyde with a hydroxyl group and an ether on the ring. And Raspberry ketone. Dr. White loves raspberries. I'll show you the structure right now. And if you notice, this also is an aromatic compound. And remember, when you see this on the internet, like here in Wikipedia, every bend in a line is a carbon and every end in a line. So right over here at the end on the right, that's CH3, carbonyl, CH2, benzene ring with the hydroxyl group. And if you like raspberries, Dr. White does, this is what gives it the taste and smell. How does that do that? I have no idea. I'm an organic chemist. I know very little about that aspect of, I guess would be called medical science, how your tongue works to relay different tastes and sensations to your brain. Interesting work, but I like playing with atoms and putting them together and make things. So that's why I'm a synthetic organic chemist. Again, switches off onto that slide. All right, let's move on. How do you make aldehydes and ketones? Next two reactions I can go through real quick because we already did this in alcohols. If you take a primary alcohol and oxidize it, you'll get an aldehyde. And since you haven't memorized this, maybe I'm going to help you out. Don't tell anybody I'm being nice. And it's your turn. What would be the organic product or products for the following reaction? 3 points each. And don't forget, keep up with the problem sets. Don't fall behind. Do them on your own. That way you'll do well. And that way it'll make me happy. And more importantly, that will make you happy. Ooh, that's a new thing. You happy. Wow, dangerous fingers here. Time to vote. Speaking about voting, next Tuesday is a primary election here in Illinois. And brave men and women have died so you can and I can vote. I will be voting. Actually, I got my absentee, or not absentee, mail-in voting. They don't call it absentee anymore. And I'll get that in tomorrow, which will get to the voting place in plenty of time. All right, it's time to get moving. How do you do this problem? You look at the molecule and look for what's different, what's not carbon, what's not hydrogen, should get your attention. Ooh, an oxygen with a hydrogen and a carbon, and it's got only one R group on it. That's a primary alcohol. And I'll never ask on a test what's a primary, secondary, tertiary alcohol. And what do you get in aldehyde? This is my R group. Another way of thinking of it is, do you break carbon-carbon single bonds? No. So I have 1, 2, 3 across plus a methyl. 1, 2, 3 across plus a methyl. The carbon with the hydroxide group, alcohol, is the carbon of the carbonyl carbon in the aldehyde, which is this one. So it'll be double bond to oxygen, hydrogen. I know there are 4 bonds to carbon, and I can fill these in. And I'm done. As I mentioned, on test 2, there will be about 3 syntheses on any of the problems I say can be synthesis. Epoxides will not be on that. And there are 4 others I'll say can't be synthesis, but this can. And the question is, what do you oxidize? And that O in a bracket means oxidizing agent. There are a number of them, but I'm just asking you to learn that in general to make that molecule. Your turn. Hint. Make sure you're memorizing these general reactions, please. Don't forget, at 3 o'clock tonight starts National Students Turn On Your Webcam Day, or evening, afternoon, something like that. That work? Excuse me. Smooth tea. All right, let's get going. How do you determine what do you react with an oxidizing agent to make this compound? Well, you look for what's different, what's not carbon, what's not hydrogen. Ooh, an oxygen. And it's double bond to carbon. That carbon has a hydrogen. And all these carbon hydrogens here, which I'll call R. And what do you react with an oxidizing agent? O in the brackets to make that a primary alcohol. Now, if we look at this, since do you break carbon-carbon single bonds? No. You have 1, 2, 3 carbons across. And then on this carbon, you have the 2 methyl groups. And this carbon here is this carbon here. So I do that. And I know there are 4, yes, 4 bonds to carbon. And that's one way to do it. The other way is same thing. Here's an aldehyde, aldehyde. You need a primary alcohol to oxidize. Here's my R group, a T-butyl, even though in the name. Then you have CH2OH, and you put in the hydrogens. Whoop, I got to move this down a little. And there you are. All right, let's move on. Again, we've already gone through these two. If you take a secondary alcohol and oxidize it, you'll make a ketone. And here's the question. What's the product or products for the following reaction? And in case you haven't learned it, I'll help you out. Won't do this on a test, but I'll do it here. And there you go. And later this afternoon, I'll make visible the lab will do on tomorrow, Thursday, which if memory serves me correctly, hopefully it is an alcohol lab. It's really fun. All right, let's do this. What do we have here that's different? What's not carbon? What's not hydrogen? Ooh, an oxygen with a hydrogen on a carbon. That's an alcohol. Notice this carbon right here has carbons here and here, and I can call that R prime and R double and R prime, that R and R prime, getting ahead of myself. And they're connected together in this ring. And when you oxidize it, you lose this hydrogen, and form a carbon-oxygen double bond. Do you break carbon-carbon single bonds? No. So this is going to stay the same. This carbon is where the hydroxyl group, which is now this carbon, and that's how you do it. And this one I could also give in a synthesis, and I'll let you play with that on your own. Let's move on. And now a new reaction. And remember in test one, you learned Friedel Crafts alkylation. The same two chemists also invented Friedel Crafts acylation. Now, this will never be on a book, on a test, and on a book. What am I thinking? And this is called an acyl group, R carbonyl bonded to something. And that's what this does. It puts an acyl group on a benzene ring. And this is an excellent way to make aromatic ketones. So I have a benzene ring, and this is called an acid chloride. I wish I had more time this semester. This is a neat functional group, but I don't. So, and here you have the catalyst, like you've seen before, aluminum chloride. You lose this, and this carbonyl, which is right there, is bonded to the benzene ring, and you've made an aromatic ketone. Getting ahead of myself. And it's my turn. What would be the product or products, organic product or products for this reaction? Well, what do I have that's different? Oh, a benzene ring, that's different. Remember, don't forget the bonds inside. And then carbon-carbon carbonyl with a chlorine on it, acid chloride. And, ooh, aluminum trichloride catalyst. And you put the acyl group on the benzene ring, which is why it's called acylation. So what's my R? 2 carbons. So I have my benzene ring, carbonyl, my R group, 2 carbons. And that's how you do it. Let's something, instead of rushing through something, I'm going to give you, it's a Wednesday bonus day. Let's take an extra minute or so to our break and come back at 2:50. We'll start again then. So let's take a break, and I'll see you in about 6 minutes. See you. It's going to work that way. Now it'll work. Time to get going. We're talking about making aromatic ketones by Friedel Crafts acylation. And let's go. I have 250. I should have been 255. I apologize. Yeah. All right. So if we look at this reaction, benzene ring, it's called an acid chloride. It's another functional group that I wish I had time to talk about, but I don't. So I picked the ones that I think are more important to your daily life. All right, your turn. And the question is, what's the product or products for following reaction? Again, what's the product, organic product or products when you react this with this catalyst? All right, I think everybody's done. Let's get going. And the question is, how do you determine what's the product? Well, you look for what's different. A benzene ring, that's different. I got my attention real quick. And then carbon, carbonyl, carbon double bond with a chlorine, and acid chloride. And then we have a catalyst, aluminum trichloride. And what do you get? An aromatic ketone. Don't forget to put the lines or circle inside that ring. Otherwise, that's cyclohexane when it's wrong. And now, what's my R group? These 3 carbons. So I'm going to have my benzene ring, carbonyl, which is this right here, then my 3 carbons. And there you go. Oh, let me show you one more. That was weird. The 3 didn't stay where it should have. The twilight zone, do. But anyways. And I'm going to do this one. What do we have here? A benzene ring. And what do we have here? A benzene ring, but a benzene ring won't react with another benzene ring under these conditions. Yes, there are cases, but we're not going to cover it in this class. But I also have a carbonyl with a chlorine on it. I have an acid chloride. Just so happens, this is my R group. And when you react that in the presence of aluminum trichloride, you get an aromatic ketone. What's my R group? A benzene ring. So benzene ring, don't forget the lines inside the bonds. Carbonyl, what's my R group? Another benzene ring. And don't forget the bonds, or you could put a circle. Now, let's take a look at this molecule. It's got the common name. I don't know if that's also a UPAC name, benzophenone. Now, one of the things I've been saying we'll do more and more is answering the question, why am I learning this stuff? Well, the obvious answer is you want to get a grade in this class because somebody said you have to take this class to get into a program or a school. But why are you learning this stuff? Well, the reaction we just did, as I've said all semester, these reactions help organic chemists make molecules you use in your daily life. And what's benzophenone? It used to be used, it's been replaced by similar molecule, but not the same. For many, many years, benzophenone, because aromatic ketones, especially that one, has a property of absorbing UV energy, was found in sunscreens and suntan lotion to protect your skin from the harmful UV radiation of our sun so you don't get skin cancer. Not a bad thing. Now, about 15 years ago, somebody found there was the tiniest, can I get any tinier? Possibility that that might be a minor carcinogen, causes skin cancer. So first the EU, European Union, then the United States said that we can't use that in sunscreens. So they found if they popped a methyl or another small group like an ethyl on one of the benzene rings, it was different and it wasn't as carcinogenic, I guess. I don't know. That's not my area of expertise. Is a molecule a really bad carcinogen or not? And that's used for absorbing the harmful UV, I like that, harmful UV light, which is not a joking matter. My brother-in-law and his son, my nephew, had very sensitive light skin, and they could get, and one did get minor skin cancer from just being on the sun without enough protection. Very fair skin. I can go out there and get burned, which I don't, and I don't get skin cancer, luckily. Now, another use of aromatic ketones is as photosensitizers. Photosensitizers. There's a whole branch of organic chemistry called photochemistry. That's where you shine light on something and do a chemical reaction. And it undergoes, usually the light is high energy, UV. And to make the reaction go, you have an initiator, photoinitiator. And generally those are aromatic compounds. Now, where is that important? High-speed printing. They put the ink on the paper real quick. It's got an aromatic ketone. It's got molecules that will cure by photochemistry. Boom, it's dry. Not dry, it's cured. Now, give me a thumbs up. Have you ever used that real super durable nail polish that you put under the light to cure, meaning harden? Anybody out there? You can see I polished my nails this morning. Not. That also has aromatic ketones in it to absorb the energy of the UV light and transfer it to make a reaction happen. And that's organic chemistry. And that's why you're learning about these things. All right, let's do one more thing, mainly because it's fun. This molecule is called acetophenone. How it got that name, I don't know, but that's the common name for that. What two things would you react with aluminum chloride to make this molecule? That's your turn. One thing I should tell you about test two, and probably sometimes Thursday or Friday, I'll post information about test two and I'll go over it on Monday. But I will tell you something in a minute. Maybe a minute and a half. All right, let's get going. How do you do this? Well, in this case, to find out what two things you react to make this molecule, you look at it and say, what's different? Ooh, carbon double bond to oxygen. Remember what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Ooh, an aromatic ring. And what do we have? And this I'm going to call R. We have an aromatic ketone. And what do we react with aluminum trichloride? Benzene ring. Don't forget the three lines, bonds or a circle. And an acid chloride, R carbonyl Cl. Well, one of these question marks is a benzene ring. Then here's my R group, methyl. And that acid chloride, this right here, is the other thing you react to make this molecule. And that's how you do it. Now, as advertised, I should do this right now, and I'll try and do it by Friday morning, sometime by noon, if not sooner. I'll put out information test 2, but I will tell you test number 2 will cover alcohols, thiols, and then ethers, epoxides, aldehydes, and ketones. Let me write that down in case you want to see it. Most people are better visual than auditory. So test number 2 will cover alcohols, thiols, ethers, reactions of ethylene oxide, and aldehydes and ketones. And anything on this test, I'll talk about the concept in the lecture, at least 2, probably a lot more. 4 or 5 usually I'll try and hit. And we'll have a little different here. And what the difference is, and this is approximate, and I'll give you the exact. Like I said, I'll come up with the exact numbers. All right. This is approximate, but I'll get the exact out. I think it's 9 pages. I forgot how many problems. I got to finish writing it up. But historically, about 15%, give or take, some real world questions, about 35, 40% nomenclature. Nomenclature, 2 types. One type is, here's the molecule, give me the IUPAC name. The other type is, here's the IUPAC name, or now you've learned some common names, draw the structure. And finally, 7% reactions, where the bulk of those are, give the organic product or products. But 3 will be synthesis. What are the starting materials used to make this compound? And like test number 1, test number 2 will have 5, 5, 5 bonus points. Now, not to scare you, but this will. Historically, test 1 is the highest. Historically, test 2 is the lowest average of the semester. Now, a couple semesters ago, I actually had 2 semesters in a row where test 2 is a great class. I hope you're a great class, was a little higher average than test 1, which was quite good too. Wow, those were good classes. And I hope you are too. All right. Well, that's Friedel Crafts acylation. Let's move on. Now, let's talk about the Carbonyl group. Remember, you should know how to draw the carbonyl group, carbon double bond to oxygen, and name it. What is it? Carbon double bond to oxygen, or carbon atom double bond to oxygen. Now, it turns out, and for this slide, click, the switch is in the off position, but this is good background information to help you understand what I'm going to talk about when I go click. Now, oxygen is more electronegative than carbon. What does that mean? That means we're sharing electrons in that double bond, but I'm stronger than you, oxygen says. Let's share them closer to me. And because of that, the pi bond is polarized. Remember, any double bond in organic chemistry, 1 pi bond, ooh, a fancy pi, and 1 sigma. Now, what that means is the electrons in the pi are a little closer to the oxygen than the carbon. It's pulling it closer. And so a carbonyl carbon really looks like this. And what this delta means is slight. There's a very slight positive charge on the carbonyl carbon, carbon bonded to oxygen, double bonded, and a very, very tiny negative charge on oxygen. But that provides an important ability, and that is to ketones and aldehydes to undergo nucleophilic attack, and it happens at the carbonyl carbon. Nucleophilic. I know the word phile means lover, nucleus, nucleo. Oh, nucleus. What's the charge of a nucleus of an atom? Positive. And therefore, nucleophile means positive, loving, intermediate. And where is it going to attack? Where is it positive? Right there, the carbonyl carbon. And what happens is the electrons go to the oxygen. Switch is still off, and we call this nucleophilic addition to carbonyl group. And if I had a nucleophile with a negative charge or other types, it attacks that carbonyl, and the electrons open up and go on the oxygen. And you get this intermediate, which you can protonate, add acid to make that hydroxyl. And here's an example showing a little, sometimes nucleophiles are H plus Nu minus. Nu is shorthand for nucleophile. And here, all the fun happens at the carbonyl carbon. That's why, what was it, Monday, I think I said, if somebody asks me, what kind of organic chemist are you, Dr. White? If I'm really honest with that person, there's only one answer. I'm a carbonyl synthetic organic chemist, and I am. Now, let's look at the next first reaction. But before we do, everybody take a deep breath, let it out. Take a deep breath, let it, I like the hands going like, let it out. Take a deep breath, let it out. I do that in a classroom too. And I'll laugh at it too. Relax. Listen carefully. The next four reactions, relax, are some of the hardest I'll talk about this semester for students to do correctly. They do with practice, but it takes a little practice. But these are important. We'll come back to them. The next two reactions is how Mother Nature makes starches. And then add two reactions after that is how your body breaks down carbohydrates, starches. And when we come into carbohydrates or starches, I'll show you specifically how your body does that and how Mother Nature does that. But for now, let's look at the following reaction. And this is the formation of a hemi-acetal, hemi-ketal. You don't have to know the names, but I'll use them. All right, here I have a, now, one of the things that happen, I don't really have it written here properly. This is the way it should be. I have it over here, but I'll be doing this right here. If R prime is hydrogen, it's an aldehyde. If R prime is carbons, it's a ketone. So this reaction works the same way for ketones or aldehydes. And you take and let me put it on the other whiteboard so you can see the carbons that my software took out. And that is, if you have an aldehyde or ketone, when R prime is H, it's an aldehyde. When R prime is carbons, not H alone, it's a ketone. And you react it with one molecule of an alcohol, and you need acid catalyst. That's what this is. And when you do that, keep your eye on the carbonyl carbon. What's attached to it comes along for the ride. And then from the alcohol here, OR and OH on that, what was the carbonyl carbon. And this is how you make a hemi-acetal or hemi-ketal. This reaction and the next three, I will never, ever put on as a synthesis problem, get the starting materials on my test 2 or any of the other tests in the final, because that's cruel, unusual punishment. I think that's still outlawed by a Supreme Court. All right, let's do one. Oops, I don't want that here. And the question is, give the organic product or products for the following. If we look at here, what's different? Ooh, carbonyl. It's got an R hydrogen here. It could also be R prime, but it's a hydrogen. And right here, what do I have in the carbonyl carbon? I have R prime. And then this molecule right here, what's different? Carbon-carbon hydroxy group. Oh, that's an alcohol. Now, here's how you do this. General reaction. What's attached to the carbonyl carbon, one of this should be double prime, sorry. That's like X, Y, and Z, is still attached to the carbonyl carbon. And if R prime was a hydrogen, it'd be a hydrogen. It is in this case. And then you break open the pi bond here, and you have OR, OH, and that's how you do it. So if I look here, this is R double prime, this is R prime, And then what do we have here? R. What's attached to the carbonyl here will still be attached. Our prime is hydrogen. Our double prime is methyl. And now you open up the carbonyl, you get OR and R here from the alcohols, ethyl. And here this becomes an alcohol, hydroxy group. But this is called a hemi, in this case, acetal. Sorry about that. Just trying to get my eraser and I clicked on the wrong thing. And to your turn, what would be the product or products of the following reaction? Again, this is a challenging reaction. So relax, you'll get it. Practice makes perfect. Oh, excuse me. I got up way too early. All right, I think it's time to do it. Let's do it. Now, if we look at this right here, the first compound, what do we see? What's different? Ooh, oxygen, double bond to carbon. Carbon's here, I'll call that R prime, but it could have been a hydrogen. And carbon's here, I'll call that R double prime. This is a ketone, but if R prime was hydrogen, excuse me, that would be an aldehyde. Then if we look here, ooh, carbon with the hydroxyl group, that's an alcohol. And acid catalyst, that's what the H plus is. Keep your eye on the carbonyl carbon. This carbon, what's attached to it, our prime or H, our double prime is still attached. Now this part opens up and the OR goes on to carbonyl carbon like this. Then this becomes OH, and this is called a hemi-acetal or hemi-ketal. So let's go up here. This is my R prime, R double prime, and R. Keep your eye on the carbonyl carbon, becomes this carbon, what's attached to it, R prime is still there. R double prime is still there. And then it has the hydroxyl group, oxygen, and what's our R group? Methyl. And that's how you do it. Oh, let's do another one of these. And there you go. Oh, let me write the general reaction because you may not have learned it yet. Now, I'll give you a little hint. I did say it was going to be a little hint. And I forgot to do this. Oh no, he fell down on the job. Sorry. Now that should help you. Bad, Dr. White. Sorry, my mind was wandering. Oh, get back in my brain, my head. Again, this reaction I will never put on the ester vinyl as a synthesis problem. That's cruel, unusual punishment. That's outlawed. Wow. Did I forget to relaunch this? I think I did. Let's try that again. Uh-oh, where'd you go? I don't know how that happened. Sorry about that. All right, looks like everybody's done. I'm gonna get to work. All right, now, what do we have here? Carbon, double bond oxygen. Look for what's different, what's not carbon, what's not hydrogen. I've got carbons here and here, and more here and here, and they're connected together in a ring. This is a ketone. And I have carbon-carbon hydroxy group, and I forgot the acid catalyst. That's bad, Dr. White. I won't make that mistake again today. And what do you get? You get this reaction where you make a hemi-acetal or ketal. What's attached to the carbonyl carbon is still attached. Do you break carbon-carbon single bonds? No. And that's still attached. This carbon right here is this carbon. What's on there? Well, we've already got our prime and our double prime. I call this our prime and this our double prime, and they're connected together, which they are in the ring. Now on that carbon, you have a hydroxyl group, oxygen, and what's my R group from the alcohol? In this case, ethyl. And I'm done. All right, let's move on. Now, in this reaction I just talked about, oh, come on, hold on, time out. Well, I ran out of memory, I think. Still waiting to get new stuff put in here, which all right. All right, back to work. Sorry about that. All right, now we have just gone through this reaction, ketone or aldehyde with one molecule. Remember, when there's no coefficient here, it's the number one molecule of alcohol with acid catalyst. What happens if you react it with two molecules of alcohol? And this is how Mother Nature forms starches. And what we start with is a ketone or aldehyde, two alcohols, acid catalyst, and here's my carbonyl carbon. And now it has two OR groups on that carbonyl carbon. And what was attached here, our primer hydrogen or our double prime are still there. And like I said, this is how Mother Nature makes all the starches. If it wasn't for this reaction, oh, I got it. We wouldn't have all the good things in life like French fries, pizza crust, or my favorite, sour cream and onion Lay's potato chips. You didn't have that reaction? Nope, that's all gone. Oh, is that sad? But I really need that stuff like I need a hole in my head. Anyways, I still like it and I eat it, try to in moderation. like almost never, because I don't need it. All right, let's get back to this reaction. And again, this will never be a synthesis problem. And now you have to remember, are you using 1 or 2 molecules or moles of an alcohol, acid catalyst? If R prime is hydrogen, then it's an aldehyde. If R prime is carbons, it's a ketone. Now, like the last reaction, what's attached to the carbonyl carbon, R prime or H, and R double prime are still attached. But since we have 2 alcohols, you have 2 oxygens, and each oxygen has the R group from the alcohol. And you also get water, but that's inorganic. So let's take a look at this in real life. Not with an R group. And if we look at what's the organic product or products of the following reaction, let's look at this. What's different? Ooh, carbon with a double bond to oxygen. Carbonyl. It's got a hydrogen that could have been R prime, but it's a hydrogen. And over here, we have carbons, R double prime. So I'll call this R prime, R double prime. Ooh, this is important. I usually don't see that. 2 of these got a carbon, oxygen, hydrogen. That's an alcohol. Acid catalyst. And what do? Keep your eye on the carbonyl carbon. Becomes this carbon was attached to an R prime or H, and our double prime is still there. You'll have 2 oxygens, and then this group I'll call R is are on these 2 oxygens. So keep your eye on the carbonyl carbon. I'll draw that first. What's attached to it, R prime, hydrogen. What also is attached to it, R double prime, 2 carbons, ethyl. Again, this carbon is this carbon right here. And what's on there? 2 oxygens. And R here comes from the alcohol, and that's CH3. And that's what you get. In this case, a hemi, that would be not hemi, acetal, not hemi, but acetal. And that's how you do it. Now, again, this previous reaction and this reaction are important, allows Mother Nature to make starches and also some other carbohydrates from the first reaction, and this one too. So they're very important to our daily life. Speaking about our daily life, if I look at the clock, it's about time for our breaks. I'll give you an extra 30 seconds today. Let's see if I get it right this time. And 45 plus 5 is 50. Please come back at 3:50. And it's time for a break. Guess what I never did? Oh, somebody should have turned on your mic. This is Dr. White making mistakes day. I'm going to try and empty. I'll come back right after break. We'll go over that again. Okay, let's take a break. I need it. I think so. See you in 5 at 3:50. Let's get going. All right, important thing. And it's not the first and it won't be the last time I do it. Once in a while, and this is a bad thing about Zoom, I think you're seeing what I'm seeing on screen, and you're not. And because right at the bottom of my screen, it's only about that big, a number pops up where it says chat, I'll miss it, especially if I'm looking here as opposed to down here, right over there, I'll miss it. So if I'm writing on the board and I think you're seeing it and you're not, turn on your microphone and say, I'm not seeing that. Let me know. That's always a safer way. And all of you have the ability to turn on your mic. What I do, and I learned this first time I taught on Zoom with a group of more than one person, is if everybody has their mics on, there's a lot of background noise and distraction. Especially in the past, I've had students in their kitchen with their kids running around or their dogs or whatever. So let's go back and repeat what I thought you saw and you didn't. All right, let's look at this reaction again. Thumbs up, people. Can you see me writing on the whiteboard? Thank you, Jordan. Now, if you take an aldehyde or ketone, if R prime is hydrogen, it's an aldehyde. If R prime is carbons, it's a ketone. And now we reacted with not one, but two molecules of alcohol and acid catalyst. Keep your eye on the carbonyl carbon. What's attached to it, our prime or hydrogen and our double prime are still there. And the two tells you you're going to have two oxygens and the R group from the alcohol will be on each oxygen. So let's take a look at this reaction. And here we go. Now, let's look at what's different. If you notice in the first molecule, ooh, oxygen double bond to carbon, carbonyl. And I'll put that down. I have a hydrogen here, could be R prime, but it's a hydrogen. I have carbons here, I'll call that R double prime. So this is R prime, this is R double prime attached to this carbonyl carbon. Then, ooh, the number 2, that's rare. See that in a reaction in this class. And we have carbon, carbon, carbon hydroxyl group, alcohol, acid catalyst. Now notice the hydroxyl group is on the end carbon of that alcohol. And what happens, keep your eye on the carbonyl carbon, what's attached to it, our prime or hydrogen, stays attached. Also our double prime. The 2 tells you there's going to be 2 oxygens on that carbon that was the carbonyl carbon, now is this carbon. And on each carbon, our oxygen is the R group from the alcohol. The carbon with the hydroxyl group will be the carbon this oxygen is bonded to. Again, the carbon in the R group with the hydroxyl group, OH, will be the carbon this oxygen is bonded to. So this is my R group. And let's put this all together. I'm going to draw what was the carbonyl carbon, which is this carbon right here. What's attached to it, R prime, is a hydrogen. Our double prime is a methyl group. Then because of the 2 here, we have that. And now what's our R? 3 carbons and propyl. And there's the molecule you get. And now I'm going to let you have fun with this. And there you go. Have some fun with this. I'll give you a little extra time because it's a hard reaction. And again, I will never give you a synthesis problem with this reaction. And remember, please be patient. I try and give everybody a chance to finish. All right, I think everybody's finished. My turn. What's the product or products from the following reaction? Well, we look at this and say, what's different? Ooh, oxygen, double bond to carbon, carbonyl. It's got carbons here and here. I'll call that R prime. Could have been hydrogen, but it's not. I got carbons here. I'll call this R double prime. And then, ooh, that's unusual. Number 2, carbon hydroxyl group. I'll again look for what's different than oxygen. And what do we get? An alcohol. And I have acid catalyst H+. Keep your eye on the carbonyl carbon. What's attached to it? R prime or hydrogen, and R double prime is still there. Now, 2 alcohols makes me say to that carbon, 2 oxygens, and then I have my R groups from the alcohol. And what's my R methyl? So this carbon right here is this carbon. Well, no, this carbon right here which becomes this carbon. So I'll draw that in. What's attached to it, R prime, ethyl. What's also attached to it, R double prime, and that's methyl. Then, because of the two, I have two oxygens. And then what's R? CH3, CH3, and I'm done. And that's how you do it. Now, a while ago, first of all, I'll give you a second or two or 5 or 10 to copy that down or check what you did. Also, don't forget, if I move too quickly, you can either ask me, could I see that again? Or you can also come back and watch me on my YouTube channel. Yay, I'm a YouTube star. Not really. Now, I'd said first day, and I might have mentioned again, this semester, you'll learn some things about me. Well, I was fortunate enough to be in the research group and have as my PhD advisor, Dr. William Roosh, who I will forever be grateful to. I don't think he's still alive. I haven't talked to him in a couple of years, but he taught me and other people in our research group how truly to become a synthetic organic chemist and lay a strong foundation that the rest of my life I've built on to become the organic chemist I am now. Synthetic organic chemist, carbonyl synthetic organic chemist. Now, Dr. Roosh got his PhD by a great organic chemist, Herbert Stork, Dr. Stork, in I think University of New York. I forgot which one of the University of New York or New York universities. But anyways, he got his PhD from Dr. Stork. And Dr. Stork had done some great things. Dr. Roosh did very good things, but Stork, Dr. Stork, is well-renowned historic organic chemist. And one of the things he found needed to do was certain reactions will attack ketones and aldehydes when you don't want it to. So how can you protect them? Think about if it's raining outside, it's not now, but if it was, and you wanted to go to your car, or say you're in your car, let's say go to your car. And how would you stay dry to go from your house to your car if it was outside, or from a building to your car? You'd use the umbrella or maybe a raincoat. Let's say an umbrella. Pretend I have an umbrella. Use your imagination. Anyways, the umbrella would protect you. And when you got to your car and got in, and it was still holding it so you don't get wet when you get in, do you take the umbrella and still hold it over your head in the car? No, you're done with it protecting you and you get rid of it. You fold it up. Well, Dr. Stork found a really elegant, and organic chemists use terms elegant, beautiful, and they are. Now, you know I'm an organic chemist, for certain reactions that people invented. And here's the one that you should take a look at. All right, everybody see what I just wrote on the whiteboard? Aldehyde or ketone? I'm being hypersensitive today. So I already messed up with you. Can you see it? Thumbs up, people. Thank you, Jimmy. All right, now what Stork, Dr. Stork, came up with to protect aldehydes and ketones was this reaction. Now let's look at what we have here. Here we have an aldehyde or ketone. If R prime is H, it's an aldehyde. And R double prime. And let's look at this. This is ethylene oxide, not ethylene glycol. And what does it have? Ooh, hydroxy group on a carbon and alcohol. Another hydroxy group on a carbon, alcohol. And I can just say that's this. Two alcohols, as the catalyst, but the R groups are connected together right here to here. And what do you get? Well, keep your eye on the carbonyl carbon. What's attached to that carbon is still there. Ooh, the number two, and remember, this has that and that, which are two alcohols. And you have OR, OR. Now, in this case, they're connected together. So let's take a look. What's attached to the carbonyl are prime, double prime, and R prime, which could have been a hydrogen. And then two oxygens. But now what's R? This. Do you break carbon-carbon single bonds? No, don't forget it's still there. For whatever reason, students forget to put that bond in. There, don't forget, students forget that. And that's a protecting group. And it's easy to put on, it's a high yield reaction. And I'll show you how when you're done doing something else, like an umbrella, you can stop using it, or like a raincoat, you can take it off. And that's the beautiful advancement of organic chemistry that Dr. Stewart discovered or created. So let's take a look at one for you. Your turn. Hint, hint, don't forget. There's one bad thing about Zoom. If I were in a classroom, I could just look around and see, is everybody done? All right, let's move on. And if we look at this reaction, we look for what's different. Ooh, remember what's not hydrogen, what's not carbon. You get your attention like this. All right, we have, an oxygen, double bond to carbon, carbonyl. It's got a hydrogen that could have been R prime, but it's a hydrogen. And we have our double prime carbons. So I'll call that R prime, our double prime. Ooh, what's different? Oxygen, a hydrogen, and a carbon. That's an alcohol. But there's a second oxygen, a hydrogen, and a carbon. And that's two alcohols in ethylene glycol. And acid catalyst. And what do you get? Keep your eye on the carbonyl carbon. What's attached to it, R prime and hydrogen, our double prime is still there. Then because of the two, we have two oxygens and R and R. So this is my R group, but don't forget there's a bond between them. So carbon, this becomes this carbon. What's attached to it stays attached to it, H, oops, H, and then my R prime is ethyl, two carbons. Then I have, because of this, two oxygens. Two oxygen, each one has CH2, but don't forget the bond between here. It's still up here. It's still going to be here. And you put on that protecting group. And that's how that works. Oh, let's do one more in general. And here's one more for you to try. Enjoy. And while you're doing this, these two reactions, this one, the one I did earlier, with one molecule of alcohol, ROH, will never be a synthesis. And also, since these are challenging, I'm going to go back tomorrow and spend a little time reviewing this. And I think we'll get to one of the other reactions of the four that are challenging at first to students, but you'll get it. And don't forget, tonight from 6 to 7, I'll have my office hour on Zoom. So if you have any questions, always feel free to stop by, say hello, and ask your questions. And I'm there to help you. And time for a little Dr. White hint. I did say little. I don't know if I relaunched this, so I'll do it again. I don't think I did. And the answer is, looks like everybody's done, so I better get to work. Let's take a look at this molecule. What do we see that's different? What's not carbon? What's not hydrogen? An oxygen double bond to this red carbon. And what do we have? Carbons here and here, and here and here and here, and they're connected together. I can call this R prime, and this R double prime, or you can do it the other way around. And what do we have? A cyclic ketone. But it could have been an aldehyde. Now, it just so happens this molecule, they're connected together. Ooh, two of carbon-carbon OH, two alcohol, acid catalyst. Keep your eye on the carbonyl carbon, what's attached to it, our prime and our double prime, and I'm getting ahead of myself. Keep your eye on this carbon, what's attached to it, our prime or hydrogen, our double prime. Then because of this, I'll have two oxygens, and each one has the R group from the alcohol. What's R? This. Now, with the ring, do you break carbon-carbon single bonds? No. So now the carbon double bond to oxygen will be this carbon, which is this carbon. You'll have two oxygens. And what's my R? Right here, ethyl. And each oxygen has that, and that's what you get. And that's how you do it. Now, the question is, when you make molecules like this, what can you do with them? Good question. Thank you, Dr. White. Now, before I answer that question, I have a question for you. And I'd ask the same question if we were in a classroom right now, not a lab classroom. And I'd ask everybody, if I needed acid and water, real quick, where would I find acid and water? Anybody? You can use chat if you don't want to turn your mic on. Right now in my room or where you are sitting right now, where would you like that? Find acid and water, H plus and water. And the answer is your stomach. Your stomach, you can't see mine, but it's down here somewhere. It's right there. But anyways, your stomach. One of the miracles of life to me personally is I have cells and you have cells in your stomach that make hydrochloric acid, H plus. And if you've been drinking the amount of water doctors tell you to drink, and I try to, you also have water in your stomach. And that's an acid catalyst or acid and water mixture that helps break down your food. The reactions I'm going to show you are some of the general reactions, how your body, your stomach, and I think someone corrected me. I think it was, I forgot which intestine, it also breaks it down, and to things your body needs. What does it break down with these next two reactions? Carbohydrates, the good stuff in life. Well, some of the good stuff. And let's take a look at that reaction. Now, the first reaction I call reversing. You could also call acid hydrolysis of hemi-acetal or ketals. Now, here's the key thing. This and the next reaction have something in common. They have a carbon with not one, but two oxygens single bonded to it. This and the next reaction are the only places in organic chemistry where you have two oxygens that are single bonded to a carbon and other stuff on there. And notice here, I have water and acid. I could also write it like this, which I sometimes do. And what you get back is the aldehyde or ketone you started with to make this compound, plus the alcohol you started with to make this compound. In other words, you're reversing it, breaking it down back to what you started with, which is how your body breaks down things. Oh, I better, well, first water break. I should tell you, the last time I took biology was freshman year of high school. Boy, that was a long time ago in a galaxy far, far away. But doesn't mean I don't like biology. But at that point, I knew I wanted to become a chemist. But this is the chemistry going on in your body, in your stomach. Now, what's different? Two oxygens single bonded to the same carbon with other stuff on there. What do you get back? Look at this carbon with the two oxygens. Becomes a carbonyl. What's attached to it, R prime and R double prime, and R prime can be a hydrogen, are still attached. And next, this oxygen with an R group becomes this alcohol. And you get, in this reaction, you'll also get some, no, you don't. Anyways, so let's take a look at this. Now, let's look at what we're dealing with here. What's different? What's not carbon? What's not hydrogen? Ooh, an oxygen with a hydrogen, and another oxygen with carbons. It's the same carbon. And then there's carbons on here, same carbon. Could have been a hydrogen here, but it's not. Carbons here. And this is a hemi-acetal. And whenever you see two oxygens single bonded, one line, not two lines, one line. Hold on, let me make sure everybody's seeing me. Nope, I did it again. Somebody should have yelled at me. Yell at me. Bad, Dr. White. All right, let's go through it again. General reaction. Hold on. Thumbs up, people. Do you see my whiteboard? Thank you. Thank you. All right. Carbon in this molecule, two oxygens. One has a hydrogen, one has an R group. And now on that same carbon is here, either R prime or hydrogen, R double prime, acid and water. Let me move you out of the way here, me too. You get back the aldehyde or ketone plus the alcohol you would have used to make this, which I showed you earlier. So let's look at this example. What's different? You see an oxygen? Oh no, two oxygens single bonded, one line to the same carbon. That's rare. Only this and the next reaction is where it ever happens, and they both give the same products. And I'll show you. And now, here we have, I'm going to call this R prime. It could have been hydrogen. I'll call this R double prime, OH. And the carbons on the oxygen, I'll call R. Keep your eye on this carbon with two oxygens. it becomes the carbonyl here. What was attached to it, our prime or hydrogen, or our double prime or our double prime is still there. And then this R group on the oxygen becomes this alcohol. And that's what you get. So if we look at here, keep your eye on this carbon, that becomes this. What's attached to it? Our prime methyl, our double prime methyl. And I get this alcohol. Where's the R group? Right here. So I get CH3, CH2, OH. And that's how you do this reaction. And these types of reactions, not with this specific molecule, but later when we get into carbohydrates with that one, guess what? That goes on your stomach. I'll never do a synthesis problem with this. All right. And it's your turn. Give the organic product or products, and on the test, watch closely. I'd be very nice and I do this, which tells you there are 2 products you should be getting. Your turn. Don't forget, if you haven't, turn in the lab that was due yesterday. Turn your labs. You don't want to lose easy points by not turning them in. Don't forget, another lab is due tomorrow. And later today, early tomorrow morning, I'll make visible the lab we're doing tomorrow, which, if memory serves me right, I hope it does, is the alcohol lab. And no, you don't get to drink any, not in the lab, and not unless you're over 21. All right, my turn. And let's take a look at this reaction. And the question is, are you seeing it? And the answer is yes, you should. Let's do it. What's different? Ooh, what's not carbon? What's not hydrogen? Not only one, but two oxygens to the same carbon. And what we have here is an OH group, hydroxyl, oxygen, carbons on that. Then here I have a hydrogen. It could be R prime, but it is hydrogen. And I have carbons here, R double prime. We have a hemi-acetal or hemi-ketal. I'll never ask on a test what they are. We're reacting with acid. This means acid, catalyst. And I hope we all know what H2O is. Water, aqua, in German, Wasser. And keep your eye on this carbon with two oxygens becomes this carbonyl. What's attached to it here and here is still attached to it. And then this R group is on this oxygen, which becomes this alcohol. And now this is my R prime, R double prime, and on the oxygen up here, my R group. So now I'll say this carbon becomes this carbon, double bond oxygen. What's R prime? Hydrogen. What's our double prime? Two carbons. And remember, there's 4 bonds to carbon, and we don't break carbon-carbon single bonds. And then what's my R group? Which becomes this alcohol, and that's how you do it. And I said, like I said, tomorrow I'm going to go over this again, because this one of these 4 reactions, I'll do it once, then I'll do it again tomorrow. That helps students do better, which is what I want. Now, let's look at the last reaction of these 4 that I will never put as synthesis. And here, if there's a carbon here, what do we have that's different? Oxygen, ooh, 2 oxygens to the same carbon with R groups on it. And they have R prime, which could be a hydrogen, R double prime. And what you get back is the aldehyde or ketone plus 2 alcohols. Now I put this 2 in here. You don't have to write it down, because on tests I ask, give the organic product or products for the following. So you don't have to put the 2 there. It does go there. The reason you see it on the side, you'll see me do this when I do a problem, is I had these 2 twins who are good students, but they got really, really upset if I didn't put a 2 there. And you don't have to, because I'm not asking you ever to balance the equation. But I didn't want 2 sisters. They're identical twins. And they both got upset if I didn't do that. And the last thing I need in a class is a set of twins mad at me. So I kept on, I've changed my slides, but on the test, you don't have to do that. Speaking about having to do, I just looked at the clock. Boy, time flies when you're having fun with aldehydes and ketones and Dr. White. Now, remember, the lab we did on Tuesday is due tomorrow. Again, the electrophilic aromatic substitution lab we did yesterday is due tomorrow. The one that was due yesterday is still due. If you haven't done it, do it. Well, that's a lot of D's there. Hopefully it's not your grade. Ooh, that was bad, Dr. White. I hope everybody gets A's or A's and B's. Please study. All right, with that, I've got a minute left, and I'm going to let you out a whole 60 seconds early. Actually, I was told by our dean that when I do internet like that, I had a misconception. I should give you the same FaceTime, be with you in lecture, that I would in a classroom at ECC. She said, no, you just have to meet with them 1 or 2 hours a week. And I thought, no, I want them to succeed, which is why I'm doing this. And with that, I'm going to say, don't forget, hand in the lab tomorrow, get it written up and hand it in. Don't forget, tonight from 6 to 7, I'll have my office hour. After 7, I'm going to watch the Stanley Cup final playoff game. It should be exciting, I hope. And with that, I'll say, Genghis goodbye.